All right, I am going to see about working through the math. It's kind of just a tinker sandbox kind of session, just practicing working through the math and trying to just practice recalling it really, and just seeing how it goes. Just to kind of put some reps in, so to speak. So we're going to be working through the math, kind of the intuition behind the values of a perspective projection matrix for OpenGL. So, wasn't that guy's name Song Ho? What the fuck? What was that guy's name? Perspective projection matrix. Yeah. Well, here it is. Wait, is that it? Yeah. I'm just finding my reference material here. So the idea is that we want to find the values of some 4x4 matrix. So we have some matrix that has, this pen's kind of weird, that has some, okay, is my eraser not working? That's not good. And these are the type of kinks I'm kind of trying to work out with these kind of testing videos. So I don't have an eraser set up, do I? Button 3, eraser. Close that, grab it, run it, do it. Boom, beautiful. Cool. Okay, so again, we want a 4x4 matrix, right? So we have essentially 16 values, and we're like, well, what do these values need to be to get the desired result, really, for doing the perspective projection? And that's obviously a big question. It's hard to just intuitively know what that means or what that looks like. So we're going to try to work through a little bit here. I wish I had a drawing software that I can scroll, and that might be the way to do it instead of doing with the grommet thing. Grommet's definitely useful in some situations, but so one, I guess again, it's hard because I don't really understand all of this that well. I'm just trying to walk through to see where I stumble. But part of the thing that we're doing is that we're taking what is considered eye space coordinates or camera space coordinates. Get my pen back. So we're taking eye space and converting it to projected space. Right? And what does that really mean? Well, if we look at this diagram here, if you look at this diagram here, we have, just trying to figure out my controls. We have this here, which is the truncated pyramid frustum, the eye coordinates. There's some point in here that is this is kind of our scene. We have some point in this scene in eye space. We are trying to convert it to what's called I believe the canonical view volume, which is a cube that is, as you can see, a 1 by 1 by 1 kind of. Well, I guess it's not 1 by 1 by 1, but it's each direction x, y, and z has a range of -1 to 1 inclusive, as you can see, kind of indicated by all of these here. So that's kind of the idea. But okay, the question is, how do we convert from that eye space to clip space? Sorry, not eye space to projected space. Well, the way to think about it is to kind of draw it out and then work through the geometry. So if we're talking about that viewing frustum from the top view, right? We're looking down at that truncated, oops. Again, still trying to figure out my controls. We're looking down from above at that truncated view of that viewing, that that truncated pyramid frustum. This is what it looks like, right? This way is our, this is our z-axis. Actually, I should probably use a certain color for that. We'll use blue for z-axis. So the z-axis kind of going this way. We have our x-axis, in this case, going this way. And specifically, this is positive x, and this is negative, or positive z. Then this is negative z. Which again, I think that sort of thing depends on your graphics API, question mark. But the point is, those are the axes because we're looking down from above. And what we have is we're gonna have some point that's in our in our scene, the I space point, right? The coordinates. So this would be some point that has the coordinates x sub e, y sub e, z sub e. That's just saying our x, y, z coordinates within the I space. And what we're saying is, hey, we have a camera right here. This is our eye, this is our camera, whatever you want to call it. If we were to draw a line, if we were to really just draw a line from our camera, which the camera will say is this point, the camera's just there for an indicator. That's the point. Where does this point line up on the, I guess this is called the viewport maybe, or the screen? Where does that point line up? Well, it lines up right here. Okay, cool. Visually makes sense, intuitively. But the question is, what's the actual math behind that? What's the coordinates for this point? So that's where we're trying to figure this out. So we know that our viewport here is at a distance of near, and we know this over here is at a distance far, because those are arguments we give to our that's arguments we give to the projection, the perspective projection function or process. Specifically, this is negative near and negative far because we're going we're at 0, 0 here, I believe. Could be wrong with that. And we're going the negative z direction right there. And the thing to recognize right here, really important, is this whole thing is it is a triangle. And specifically, it's two triangles. There's a triangle here, and we'll just use green for that. There's a triangle here, and there's an overall triangle here, because these triangles have I don't know, I guess all the mathematical terms, they're similar triangles, which means, let me go to this, which means I guess what's the mathematical term for similar triangles? It means they have the same angle or something, the same proportions. And if we were to redraw it right here, and this is of course terrible drawing, they have the same angle here, they have the same angle here because that's the same thing, the same angle up here, and all these sides are proportional. So we can really redraw them as two separate triangles not drawn to scale, and figure out, and then kind of map out what these points are. So what we're trying to figure out is the coordinates of this point right here, right? So in other words, because we're on the z and x axis, we're trying to find the z and x coordinates for this, specifically for this point right here. And this is the point that we have coordinates on because we have these coordinates up here. So we know that this right here, which is this whole thing, we know that that is, because this is a z-axis going this way, we know that's z sub e. And we know this right here is this height right here, which again, x-axis going vertically in this, from this view, this is going to be x sub e. Okay? And then we know right here, this length is negative n, because that's the distance from our camera to our viewport, or projection plane, or whatever the term is for this part. So we know that this is negative n. And then this right here, well, that's kind of what we want to figure out, because this is actually just the same as z sub p, which is our z coordinate for the projected point. And similarly here, this distance here is the projected x value, so x sub p. And these, of course, are values we already have because we know what this is. We're just using variables here. This is something we don't know the value of, we want to solve, right? So we just use proportions here to say we know that, x sub e over z sub e is equal to x sub p over z sub p, but of course z sub p we know is negative n, so we do that instead. Cross multiply, or not even cross multiply, but we want x sub p by itself, so we take negative n, multiply it to both sides, and get x sub e over z sub e times n, put the negative over here, and that equals x sub p. So we'll kind of jot that down up here. And then we're going to do a similar thing, and hopefully be a little bit quicker this time. We'll do a similar thing with the side view of the scene. So we'll just erase this, but it'll look very similar. Okay, so similar thing, we have the viewing frustum, but this time it's from the side. We're still doing the z coordinate this way. Again, that line is very not to scale, so to speak. Still positive z, negative z, but instead now the vertical, axis is the y coordinate. So we have, because again we're looking from the side now, so this is negative y, positive y. We have our camera here again. We have some point somewhere. We want to figure out, if we draw a line here, what's the coordinate of this point? This point, again, the coordinates are x sub e, y sub e, z sub e. Of course, the x value won't be relevant here because we're only in 2D. Again, similar triangle. Let's just draw those out. So this triangle is this right here. And then another one, again, not to scale at all. Not to scale at all. Is this overall triangle here. And this again is negative f. I guess I wrote negative n here, but I wrote negative f last time, didn't really matter. Just give more context, I guess. So we know that this distance is negative n. We also know that this is z sub p. We know that this distance here is x, in this case y sub p, and that's what we're trying to solve for. And then we know that this is, again, z sub e and y sub e. And these are values we actually know, so we can use them to solve for y sub e. So we can say, we can do the proportion y sub e over z sub e equals y sub p over, again, z sub p is negative n. Yeah. So I just checking my recording. Cross multiply. Multiply by negative n to get it out of this side. Y sub p equals y sub e over z sub e times n. I can move the negative over here. I say again a lot, don't I? Y sub p. This looks very similar to the other one. It's just instead of x, it's y, and so on and so forth. So that's some information that we now have as far as the overall intuitive context of this whole process, I guess you could call it. But what are we really supposed to do with that? And that's the thing I need to refresh myself on, because I don't actually fully have the intuitive understanding. So I think, if I understand correctly, one thing that's important is to recognize that, okay, the value, because again, the final thing we want is these projected coordinates, so we know, hey, once we do the whole projection process, because we can think about it this way. We can think about we put in the I space coordinates, where this is going to be, some vector x, y, and z. We put it into the black box of perspective projection. Let's call that PP. And out comes our projected points. That's the whole idea. That's what we're doing here. We have the I space coordinates that we know the coordinates of. And we're saying, okay, that's in our scene, kind of. Where does that end up on our actual our viewport, I guess? Again, I don't have the terms and the intuition down very well, but I think that's somewhat the idea. So what do we need to do to these values to get these values? That's the whole challenge. So something to recognize here is that for both these values, for getting the x sub p and y sub p, we divide by z sub e in both times. And this is where that idea of perspective divide comes in. And I believe this is the way this works in the actual like GPU graphics kind of API process, is it actually comes after the shaders, because within the shaders you have the model view projection process, which is essentially you have a model matrix, a view matrix, and a projection matrix all times the given point, and this gives you the final coordinates, I guess. Again, very shaky understanding on that. But the perspective divide actually comes after that, technically. But in the mathematical intuition of it, it's kind of baked in, right? And we need to figure out how to separate it out so that we can get I guess I don't need to draw all 16 question marks, but I guess I'm also going to figure out how that all bakes into this whole matrix. But again, the perspective divide is not technically part of the matrix, so I think at some point in the process we like kind of extract stuff out without the perspective divide, knowing that step is important, but it's going to be it's going to kind of be its own thing. So it's kind of unfortunate this Grommet MPX doesn't let you undo erasing the whole screen. So we have those formulas. Let's write those down again somewhere they're going to be out of the way. They were x sub p equals negative y sub e over z sub e times n, and then y sub p equals negative. Oh, this wasn't negative y, this was... Okay, that's not good. Oh wow, you can go back. What? Okay. Interesting. Well, I guess I just figured out a hack for that. Interesting. Very strange. So we have both of those now. What do we do with it though? What's the next step? I believe we don't actually do anything with it explicitly right away, but the next step then... Oh, okay, this actually is relevant. So recall I pointed out that we divide by z here, z sub e specifically. So that's an important step. So that means we can say for our perspective projection matrix that we need some part of the process to help us encode this z sub e value so that we can then keep it around and use it to then do our perspective division, a perspective divide step. So again, remember, the overall process here has, the shader stuff, all the like the MVP multiplication by the vertex, like I said, and then it also has the perspective divide. It's not actually all one step, so we need to make sure we still are able to do the perspective divide after we do all this step and modify the vertices in very serious ways. So the way to do that is to use the w value, right? We're going to have vertices that are x, y, and z. There's a w value, but we don't actually really need that. So what we can do is use that as the place to kind of, again, encode that z value. So what that looks like kind of in a certain way, if I can delete all this. What it looks like is that we have our x sub e, y sub e, z sub e, and w sub e. We'd multiply this by our magical, just making it red and make it real magical, our magical 4x4 projection matrix, perspective projection matrix. And this needs to lead to us having, it'll lead to us, and I think technically these are swapped, because technically you do the 4x4 matrix first, but it's fine for the intuition aspect of it. What we need is for this values end up being, you know, our x sub p, our y sub p, z sub p, w sub p. But what we actually need is for w sub p to equal z sub e. So this needs to come in, do whatever happens in this whole process, and come out still intact, so we can use that to then do perspective divide, which essentially is saying, hey, let's do x sub p divided by w sub p. Let's do y sub p divided by w sub p. Let's do z sub p divided by w sub p. And this will give us our clip coordinates, I believe. X sub c, y sub c, z sub c. Don't have a great understanding of how that works, but that's the gist of it. So we're going from I space to projected space to clip space, right? So how do we keep this around? I kind of beat that idea to death that we need to keep this value around so we can then do all this. But how do you actually do that? Well, let's think about how matrices work. Let's think about how matrices work. Right? We'd have a 4x4 matrix. I'm not going to write out all the question marks this time. Times some four-dimensional vertex. So if we want to affect this value down here, how do we do that? With the matrix works, how does what affects that? Let's just do zeros. Well, remember, let's say we're doing this first one. So we'd take this row times this column, which of course is the whole thing, and say 0 times x. This is maybe not the best case of having 0 for all of these, but 0 times x, 0 times x. Let's actually rewrite that, make it a little more clear. Let's just do AB. Let's just do 1, 2, 3, 4. So you'd say this times this would be 1 times x, so 1x plus 2 times y, 3 times z, 4 times w. Right? And this defines, whatever this ends up being, defines our x value in the new one, right? So whatever's in this row affects our x in the final output. This defines the y in the final output. This defines the z. This defines the w. Okay, that sounds important because we're trying to define the w. So that means we need to focus on the last row. Okay, so let's kind of go back and kind of do that whole process again for the final row. Go back to zeros. Okay, let's say we're worrying about this row. Let's see how this row affects our w over here. So again, let's say 1, 2, 3, 4. Multiplying this by this would be 1 times x plus 2 times y plus 3 times z plus 4 times w. Okay, so 1 affects is the x, 2 is the y, 3 is the z, 4 is the w. So this row and this column, so this element right here, well, no, sorry, this doesn't affect the W, that uses the W. What we actually want to focus on is this one right here that uses the Z, because again, we're trying to encode these are Z sub E's, Y sub E, all that stuff. This is the I space coordinates. That's what we want to use to encode over here, right? Z sub E. So we need to focus on this. So that's what we need to affect. That's what we need to modify in the perspective projection matrix. So what we're saying is, if we had 0, 0, 1, 0, then when you multiplied that by our vertex and do 0, 0, 1, 0, then what this would end up with is 0 times x plus 0 times y plus 1 times z plus 0 times w, which, you know, equals z, which means our w in the output matrix right here is just z, which is exactly what we want, because then we'll have this kept around. We'll kind of use this as a temporary, almost like a temporary register. Almost like a temporary register to keep around, and then use that for the perspective divide. And that was a very probably overly verbose, not clear way of explaining it, but again, we're kind of just wandering down a dark alley trying to figure out how to explain this stuff. So that gives us our first row of the matrix. Whoop-de-doo. We still have 3 more rows to go. So what's next? I'm going to take a quick pause here.